an institute postdoctoral fellow at School of Physics, Indian Institute of Science, Education and Research, Thiruvananthapuram during 2015 to 2016. He was a postdoctoral fellow at Quantum Information Science Group, Department of Physics and Astronomy, Seoul National University, Seoul, South Korea during 2016 to 2021. He is the co-inventor of the invention on methods and operators for linear optical quantum computing, which is applied for US patent. He has published more than 17 research papers related to quantum research in reputed international journals. Other achievements includes cleared joint entrance science screening test just physics with 99.03 percentile, graduate aptitude test in engineering gate with All India rank 203, national eligibility test with All India rank 96. Dr. Omkar Sri Krishna is an accomplished quantum computer scientist specialized in the field of fault tolerant optical quantum computing. The very nature of this job it demands a deep understanding of various scientific fields, including mathematics, quantum physics, statistics, quantum optics, and computer programming. Dr. Omkar has acquired expertise in mathematical modeling of optical systems, design state that can correct for faults and implement universal logical gates on them. He has a wide expertise in manuscript preparation, patent filing, and project management. He is working towards designing a fault-tolerant optical quantum computing in collaboration with hardware experts that can be used in many industries, including finance, healthcare, and manufacturing. Presently, Dr. Omkar is working as quantum theorist architect at Architecture Group ORCA Computing, Toronto, Canada. With this background, I welcome Dr. Omkar Sri Krishna to deliver lecture on optics for quantum information processing. Over to you, sir.
Thank you, Anand sir, for that detailed introduction. I'm really grateful for that. So I'll start sharing my screen. Can you guys see my screen?
I can see your screen.
Okay, thank you.
There is one journal paper, physical.
Oh,
That is, yes, sir. Photon sorting and efficient L measurements. That is visible.
okay. So, but you can't see my slides, right?
No, sir. No, sir.
Okay. Yeah, give me a moment. How about now?
Yes, sir. Now I can see your presentations.
And does the slide move?
No, sir. Not the full screen. Slideshow has not come yet.
Okay. Sir, how about now?
Yes, sir. Now the screen has been shared. Yeah. Now perfect, sir. You can proceed, sir.
Are the slides moving?
Yes, sir. Yes, sir. Moving, sir.
Okay.
Perfect.
Thank you.
Continue.
Yeah. Firstly, I begin my presentation thanking Karnataka Science Technology Academy for inviting me to deliver this talk. As introduced, I work as an architect or quantum theorist at Orca Computing. So people may be wondering what ORCA stands for. Usually Orca means killer whale, a big shark, uh, which is notorious for its behavior. but this is expansion for off resonant cavity absorption or coupled absorption. So this is a quantum optical phenomenon on which the idea of building a fault tolerant quantum computer was developed, and that's how we have the name Orca computing. And I did my PhD from Bengaluru. So although I got from my degree from Manipal University, I worked with Professor Shrikant, who will be delivering talk maybe on Wednesday or Thursday, I guess. And it was from Purna Prajna Institute of Scientific Research, Bangalore. So with this note, I start my presentation. So first, let me give an overview of this talk. So this talk would not be very detail oriented. It would just give a broad picture of what optical quantum computing is and what is the state of art things happening in optical quantum computing. So this is the main focus of today's talk. With this in mind, I'll begin with some introduction, broad introduction to what is quantum information processing and what are its advantages. And then I'll be talking about various platforms on which this quantum information processing or quantum computing is possible. Then I move on to optical platforms. Even within optical platforms, there are many kind of physical realizations possible. So broadly described as continuous variables and discrete variables. Then after giving a good idea of these optical platforms, we move on to how gates can be implemented in these optical platforms. And then we will talk what are the issues with linear optical platforms particularly. So here we won't be including much of the nonlinear platforms because nonlinear platforms have their own disadvantages. So we'll be mainly dealing with linear platforms, and I'll explain in future what actually linear platforms are. And then once we discuss the shortcomings, the errors, the faults with this linear optical platform, then we shortly discuss about error correction and how can we make these linear optical platforms fault tolerant. Then once we discuss these things, we will learn about how much fault these platforms can tolerate, or how given an architecture, quantum error correction architecture, how much faults can be tolerated. And then we'll also learn how we can build these complex optical systems using really fundamental resources like single photons. So we'll start from single photons and build all the way up to big lattices. So I'll give some recipe for those things. And because as I said, like these things are linear optical platforms are probabilistic, so it would have a large resource overheads associated with it, because you perform some operation with some probability it succeeds, and when some probability it fails. When it fails, you need to throw away it and repeat the process so that you get the success outcome. Until then, you need to repeat the process. In this repetition process, you would incur exponentially large overheads, which we'll see in future. And we'll briefly discuss, given the current situation, what are the possible research directions we can take in future. So with this overview, let's get into the core topic and start discussing the things. So firstly, we are here to learn about quantum computing. So what is quantum computing? So quantum computing can be broadly described as a multidisciplinary field, because it uses knowledge from various fields like quantum mechanics to computer science to statistical mechanics. So it uses knowledge from various cross fields. So it's a multidisciplinary field that uses quantum mechanical features like superposition and entanglement to solve complex problems that are not tractable by classical ones. By non-tractable, I mean the classical one needs exponentially large resources, but the quantum computers are believed to do those things at polynomial or polylogarithmic scaling. So last week, Professor Usha Devi talked quite a bit about quantum algorithms and complexity of algorithms, complexity of the problems and scaling. So today I won't be talking about them much, but let's see like if we can have quantum computing. So what are the advantages it promises? So first advantage it promises is like it can model complex molecules, reduce development time for chemical and pharmaceutical industry, because as is known, when you increase the size of the quantum system, so number of degrees of freedom increases exponentially with it. Unlike classical systems, in classical systems, the size increases only linearly. Here, the size increases exponentially. So, if we can simulate or mimic some processes of quantum mechanical nature with some simple complex system, using some simple complex system, we can get insight into the complex systems like molecules, some like big pharmaceutical um, organic molecule can be learned. Many of their behavior can be learned. And you can use it for simulating physical systems such as photosynthesis, superconductivity, and people have also been talking about using the quantum computers to simulate high energy physics, like particle physics. And these can also be used within financial institutions where the companies can optimize their investment portfolio and also improve fraud detection. And of course, these are very helpful in material science. One can use these computers to efficiently simulate batteries, better solar cells, better sensors, better catalysts, some 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 algorithms like Grover algorithms, which are very efficient in searching, which speed up the search by root n, where n is the number of elements in the unsorted data. So you can use them. If a molecule has lots of possibilities, you can search for what trait you want the molecule for and pick it up. And of course, this can also be used in healthcare. In healthcare, you can have customized treatments, you can conduct research on DNA and such things. So after understanding why quantum computing is important, so let's understand, or let's take a look at how a quantum computing looks like. So the quantum computing, if we have a block diagram for the quantum computing, we can probably divide it into three parts. In the first part, we'd have state preparation. So that is, we initialize the quantum state into certain state. So this state preparation can be quantum error correcting codes when we want fault tolerant quantum computing. So we want states that are error prone but can be corrected. Which makes them fault tolerant, and we may have some special kind of states known as magic states. It's believed that magic states really offer the quantum advantage, which we are looking for. So we may have to prepare those states and distill also. Briefly, I'll explain what magic state distillation means. And we may have lot of switching, especially if I'm considering optical quantum computing. If it's not optical quantum computing, probably you don't need much switching. But yeah, but something like superconducting qubits, they don't need much switching like optical. optical ones, because the generation process, everything is just probabilistic. So you need to post select or successful outcomes. So you need a lot of switching. And the first part would usually be kept in a cryogenic temperatures because the detectors work very well with cryogenics. And the middle part is like where computing happens. That is like you have gates, you can apply gates, you can manipulate the initial state which you had prepared in the first state. And after this, you have some detectors. You read out, that is, you perform measurements and you get lot of humongous data, like large amounts of data, and you need to do some post processing with the data. So for this, you need classical decoding algorithms, such as like if I'm using fault tolerant quantum computer, we need algorithms like minimum weight perfect matching, which are quite fast but not very accurate. And you also have some other kind of post-processing algorithms like belief propagation, maximum likelihood decoders, and such things. And this is really an active field of research. So a lot of research goes into constructing or coming up with efficient yet accurate algorithms. So one of the critical criteria under which quantum computers may work is speed of classical processing should be greater than that of quantum computer. So the rate of quantum computer generates the data should be processed. So the classical computers associated with the quantum computers must be faster or equally fast. And here I
Sorry
just
to
take
interrupt, sir.
some. Yeah.
Sir, can you hide that tool which is the screen?
Yeah, that was bothering me too. Thank you.
Thank you, sir.
Yeah, thank you. So here, even in quantum computation architecture, there are two models. One is circuit-based model, in which you just initialize the states to some simple states, and then you perform gate operations, lots of gates, like lots of unitary gates, which we would be discussing in future slides. And then we perform readout of the post-processed quantum states. So this is the model number one, which is circuit-based model. We may have complex circuits, but there is another model which is known as measurement-based model, in which we prepare really complex states. They are literally complex states, but the processing is done by just measurements, just single qubit measurements, which is extremely simple. But and we have no use of gates in this measurement model. And finally, we perform measurements again, and we just read out and post process the classical data. So these are the two models for quantum computing. And beforehand, I just declare that measurement based model is very suitable for optical architecture. So although this block diagram shows some quantum circuit, but the quantum circuit is not really essential or not really significant for optical models, optical quantum computing models. So after understanding what or after having a brief overview on how quantum computer looks, now we'll get into some details. First, we begin with quantum states. What are quantum states? If you have those are a general quantum state can be superposition of all possible states of the quantum system. Here we deal with qubits. In qubits, you have two possible systems which can be realized on any platform, and and superposition of those two possibilities make a qubit, which is analog to classical bit. We have quantum bit, and the am, am, in the amplitude of the state, that is alpha and beta, they must sum to 1. So alpha square plus beta square is equal to 1. So just to conserve the probabilities. So the moment you think of alpha square plus beta square is equal to 1, you know that this this equation represents some geometric object, which is sphere, 3-dimension. Yeah, this looks like a 2-dimensional sphere. Yeah. So, but these objects can be represented in a 3-dimensional sphere, which is known as block sphere. And if we parameterize the block sphere, the quantum state looks like this. So diagonally opposite states are orthogonal to each other. That is, they don't have any overlap. And one important point I want to highlight about the state, I guess someone last week, Karthik, also talked about this. So you can represent an arbitrary single qubit state using a density matrix. So where the density matrix has this representation, where X, Y, and Z are 2 cross 2 matrices, which have real eigenvalues, and they have their determinant is 1. So they form SU2 group. And yeah, these operators are known as Pauli operators. So using Pauli operators, you can describe any arbitrary state within this block sphere. All states on the surface of the block sphere are pure. That is, they are not statistical mixture. They are just pure quantum overlaps. But as you get into the block sphere, within the volume bulk of the block sphere, you will have mixed states. So mixed states are statistical mixtures of various quantum states. Next, one of the useful states is this magic state. This is a state along the x-axis rotated by an angle pi/4. So this is magic state. So this is just an example of one of the possible states. So these states are quite useful. It would be useful. You will see like why they are useful in future. These states would provide something known as quantumness, so which we would be describing in future. So once we learn about qubits, so here I just described a single qubit. So a system can have 2 qubits, 3 qubits, multiple qubits, like lots of qubits entangled. And here I won't be discussing about entanglement because entanglement was discussed in previous talks. And tomorrow too, probably Dr. Anand would be discussing a lot about entanglement and how you measure the entanglement. So I won't be dealing with those things now. So now, after we talk mathematically what a qubit looks like, we can now talk about how we can realize on physical platforms. So the first platform I'd be just mentioning is the superconducting platform. So you guys know, like most of the big techie companies like Google, IBM, they all use superconducting platforms to build their quantum computer. And yeah, in superconducting platforms, you can have something like Josephson junction, which is a coupled oscillator, L and C coupled oscillator. So here you can encode the information in flux. So flux are current flux in say cycle direction and another flux moving in anti-cycle direction. So these are the two states of the superconducting qubit, and because there are two states, you can form a superposition and have a qubit to realize a qubit. Next is a nitrogen vacancy center. So these are possible in some diamonds like material, crystalline materials. And of course, you'll again hear about this a lot. So I won't be discussing much on these things. And you also have a quantum dot. Quantum dot is like you can fabricate, you can deposit layers of solid state materials, and you can form a bunch of atoms which behave like individual atom, and you can excite and de-excite them, which also form, which acts like average number of many number of atoms or molecules coming together. They behave like a single entity, quantum entity with two levels. And of course, again, you have trapped ions. The atoms in quantum dot are trapped in some solid state material, but in trapped ions, you have a cavity. In cavity, you put together few atoms, and those atoms collectively behave like a single atom, and one can manipulate the state of that atom. That is, one can perform gate operations on that bunch of trapped ions. So these are some commonly known platforms, physical quantum mechanical platforms, where you can realize qubit. Next, I'll be talking about qubits, optical qubits. Today's main focus would be optical qubits. So even optical qubits can be realized on different platforms. So so one so the optical qubits can be broadly classified into two, sometimes three. A third one is just a hybrid version of first two. So first you have discrete variable states. Uh, so you can have dual rail qubits, say like you have two rails, or like uh, two wires, optical wires, which are carrying photon, but you don't know like in which wire the photon lies. So if it lies in the upper half, then the logical state would be 0. If it lies in the lower half, the logical state would be 1. And the general state of this would be like a superposition of both logical 0 and logical 1. Similar to dual rail qubit, you can also use polarization degrees of freedom of the photons, where the oscillations are confined to horizontal plane, that is horizontally polarized photon, and photons have their oscillations confined to the vertical plane, and these are known as vertically polarized photons. So a photon can exist in superposition of both possibilities, horizontally polarization and vertical polarization, and thus it forms a qubit. And yeah, and of course you have something known as GKP, Gottesman, Nil, Preskill after their inventors. These are like infinitely squeezed coherent states, which look like comb lattice. And here the logical 0 are separated by a distance of 2 alpha, and the logical state of 1 has exactly peaked in between. So these two, the undisplaced state and the displaced state, they form qubit, two states of the quantum system, which is qubit. And of course, you can also have some coherent states. The coherent states are the one which are emitted from the laser. So you can displace the coherent states either to left or right. So there are two possibilities, and there too you can form optical qubits. So one of the drawbacks about GKP state is that the success rate of generating these states are extremely low, of the order of 10 to the power of -3 or even lesser. So these are some of the drawbacks. And again, you have some hybrid states which are like which have both continuous degrees of freedom, also discrete degrees of freedom. So probably we'll show that hybrid states can be useful in resource efficient quantum computing platforms. If our main focus is resource efficiency, then hybrid qubits could be a really good candidate. So, but as the GKP qubits, hybrid qubits too are extremely scarce to generate them. The success rate of generating those states is very low. So because the success rate of generating dual rail qubits is quite high, so in the next part of the talk we'll just stick to dual rail qubits. So once we have decided that we'll be mostly sticking with dual rail qubits, we have some quantum gates. Quantum gates are the operations. So if you have some state on the blocks here, by performing these gate operations, you can move this state across the block sphere. So if you have Hadamard state, you move to a superposition of 0 and 1 states, and again you can apply some 0 states, which is rotating across the equator, and then you can again perform Hadamard gate, which would just flip it back to the 1 state. And of course, you also have some phase gates. So these are known as Clifford gates. So Clifford gates are not very difficult to classically simulate. So that comes from this theorem known as Gottesman-Neal theorem, a quantum stabilizer circuit that involves only state preparation in computational basis, Clifford gates, measurements of Pauli operators, and some feed-forward operations can be simulated classically in polynomial time. So these can be simulated classically. So they are not very difficult to simulate. So with these things, we can't get any quantum advantage. So I want to highlight the control NOT and control Z gates, which are useful in generating the Bell states, the entangled states. Okay, so we discussed about Clifford gates, and I also mentioned that they are easy to simulate, and there are some gates which are not easy to simulate classically, and those are the ones which really offer quantum advantage. So those gates are known as non-Clifford gates. So they come from different hierarchy of the Clifford algebra, and you also have some 3-qubit gates, so which are known as Toffoli gates. So they are Toffoli gates, and those really provide quantumness to the circuit because they are difficult to simulate. And these are their matrix representations. We also had matrix representation for single qubit gates and 2-qubit Clifford gates. Here is the single qubit non-Clifford gate and another 3-qubit non-Clifford gate. So these are some basic gate sets. So if we have a finite number of gates available, can we simulate all the possible unitary quantum processes? That's the question. So for that, we would be seeing, we would be learning about some theorems here. So if you want to simulate an arbitrary gate on, say, like on n qubits, say, like you have an n qubit system and you want to perform arbitrary gate, that could be any possible unitary gate. So you can perform arbitrary unitary gate if you have finite set of gates. So that is, if you have Clifford gates and you have one non-Clifford gate. Example of this universal gate set is like you can have control NOT gate, you can have Hadamard gate, you can have phase gate. Along with that, if you have access to T gate, you can in principle estimate any unitary gate with a sequence of these gates up to arbitrary accuracy. So it is not that if you have a gate U, you can literally generate gate U with a sequence of this universal gate set. So you can generate it with arbitrary accuracy. So this is the catch. So here is the theorem, which is known by the name Solovay-Kitev theorem, and this states that let G be a finite set of elements in SU2 special unity 2 such that the group generated by this finite set is dense in SU2. There is a constant C such that for any unitary which belongs to SU2, there is a sequence of gates from this set of length, which is of the order of log 1 over epsilon power c, such that the distance between the sequence of gates and the unitary target unitary is really, really small. So that is like you are approximating a unitary operator U with a sequence of gates, yes, and the accuracy being epsilon. So as you can see, if you really want very accurate gates, then your sequence, the number of gates in your sequence would grow polylogarithmically. So, and usually this theorem holds for d-dimensional state, and this constant C is around 2 for qubits, I guess. And what is the consequence of this theorem? This Kitev theorem, it explained about simulating single qubit gates. But if you want to simulate qubits, a general unitary operation on n qubits, then you would need a circuit which has elements from universal gate set of m polylogarithmic, which goes as polylogarithmic. So now with these theorems, we know that given a set of unitary gates, you can generate arbitrary gates up to arbitrary accuracy. So now we'll see like how can we implement this universal gate set fault tolerantly in our optical systems. So that would be the next part of my talk. So these are some basic gates. So these are X gate, these are Y gates, these are Z gates. So this element you see is just a beam splitter, which is partially silvered mirror, and so these are the phase shifters. The Z gate, you have phase shifters. Phase shifter is a thick, dense medium which has refractive index larger than the vacuum, so that the light in the medium slows down and it acquires a phase shift with respect to the light which didn't pass through the medium. And you have Hadamard gate. Hadamard gate creates a equal superposition between logical 0 and logical 1 state. And for the universal gate set, of course, you need this C0 gate, which comes from Clifford gate. So, but this C0, one of the drawbacks about the optical system is the C0 gate is probabilistic. That is, if you apply a C0 gate 100 times, it will succeed only 2 by 27 times. So the success rate is extremely poor. So you can't do much with linear optics. So what is the bypass? So if we can't entangle qubits, how can we build a larger quantum state, and how can we perform some operations on the state? So this is so we'll be circumventing this problem in different ways, which I'd be explaining in the upcoming slides. So we just talked about a few optical systems, and like we'll just discuss, just to summarize, what are the advantages of optical platforms. The optical qubit can exist at room temperature. So this is one of the advantages over the superconducting qubits. In superconducting qubits, you always need cryogenic temperatures. Because the photons interact very weakly, there is less decoherence. So decoherence is like loss of quantumness of a qubit. So And the optical systems provide quicker gate operations compared to coherence time. So in the given coherence time, it allows us to perform lots of gate operations like beam splitters, phase shifters, many such operations can be performed. And because it's quick, the system is also scalable. And another important thing why we focus so much on these optical platforms is it's simple. It uses only beam splitters, phase shifters, delay lines, which slows down the photons, and some detectors. So we'll learn more about detectors in future. With these optical elements, one can actually build a scalable quantum computer. So this is the advantage of the optical platforms. So after looking into some advantages, let's look what are the faults it carries. So the major fault is the entangling operation is probabilistic. I just showed the C0 operation, which is an entangling operation. It is probabilistic. So the success rate is just 2 by 27, which is extremely poor. With such low success rates, we have to pay in terms of humongous resource overheads, which we don't want. So if we want to deal with such large resources, then we need to have a lot of optical switching, which makes the physical footprint of the optical computer really large, which we don't want. And another problem is photons are lost. Uh, they just pass through some elements and they get lost. They get absorbed in optical medium. So this is one of the major drawbacks. And of course, you also have Pauli errors. I'll discuss what are Pauli errors just to give some example, just to give some overview. Pauli errors are just like random flips. So your vector 0 just flips to 1. Random movements across the block sphere are the Pauli errors. So they also have Pauli errors. So how can we overcome these things? So just to give you a flavor, how we can overcome this is like we have to start with something like 3-qubit systems. And we can perform something known as Bell state measurement, which I'll be explaining very briefly now. So if we perform a Bell state measurement, this whole system can become 4-qubit system. And if we have 4-qubit systems and we perform a Bell state measurement, you can get 6-qubit system. So in that sense, you can keep building the size of the optical system, or you can increase the number of qubits, entangled qubits within the system. So now what is wrong with Bell state measurement? So Bell state measurement is a fantastic circumvention for scaling problem. But what is wrong with it? One of the major drawbacks of Bell state measurement is the Bell state measurement itself is a probabilistic process. Although its probability is better than 2 by 27, so still its success rate is half. So half of the time, the Bell state measurement can be successful. When the Bell state measurement, so yeah, before that, these are the 4 possible Bell states. This is mode 1, mode 2, mode 3, and mode 4. All 4 modes are fed into this apparatus. Then these represent beam splitting operations between mode 2 and 3, and second beam splitting operation between mode 1 and 4. Then we perform measurements. So which is basically like we are looking for photon number resolution detectors, that is like which can see like if there are 2 photons, no photons, 3 photons, 4 photons, they can resolve the photon numbers. So what is the output after passing through the second beam splitter? So different state produce a different click pattern. So if there is 1 here, it will produce the first detector reads as 1 and the second one 2. Then you can see the last 2 states here you'll read the detectors read as 2, 2, 2, 2. In all the case, there is an ambiguity. You can't distinguish whether it was from 5 plus or 5 plus. So out of 4 states, this apparatus can discriminate only 2. So the success rate is half. And of course, this has a lot of losses. So the loss is something like eta represents the probability of photon being lost. So this is successful only if both the photons survive and they don't get lost when passing through beam splitters and detectors. And so if the measurement is successful, then you can have x and x eigenvalues, which are commuting eigenvalues. But if one of the photons is lost, you can't get anything. So now we just briefly touched upon detectors, need for detectors in bulk state measurement, and now let's learn something about detectors. So there are like two kinds of detectors. One is single photon avalanche detectors. You have a p-n junction, you bombard the p-n junction with photons, and you apply some reverse biasing, and you have a peak whenever a photon impinges the detectors, and you can just learn whether a photon is present or not, but you can't resolve how many photons are present. So these are thus known as threshold detectors, which just give the information presence of the photon or absence of the photon. But you can improve on this. So if you have a photon, incoming photon, and before passing through this detector p-n junction, if you pass it through various arrays of beam splitters, where like if you have four photons get separated in various modes, then you can use the single photon or threshold detectors. So these are also known as bucket detectors. So bucket detectors are useful in photon number resolving, and state of the art detectors which can really do sophisticated photon number resolution or superconducting nanowire based photon number resolving detectors. So in these detectors, you would have a nanowire, winded nanowires, and you have photons impinging. So if you have one photon, it would create some pulse. If you have two photons, it would create other pulse. Depending on the time separation, you can really make out whether it was two photon or single photon or three photons. So and these are really small devices. You can see some images, TEM images, tunneling electron microscopy images, which are just 5 micrometer width. So lot of this. Why my intention to show about a TM image is that we can fabricate all these elements, including beam splitters, phase shifters, everything within a chip, silicon chip. So then the silicon chips would be just like our Intel or AMD processors. So what are Pauli errors? So if you have a state, you can have random flips, random X flip, random Y flips, random Z flips, phase flips. Then your block sphere actually squeezes into a point, and this loses quantumness when it reaches the center of the sphere. That is like totally mixed state, and it has no quantumness whatsoever, because quantumness fuels quantum computing. As we know, we want to preserve the quantumness. So what can we do to preserve the quantumness? So one thing we can do is we can do quantum error correction. So I won't be going into too detail about quantum error correction, but the principle based on which it works is, you can, if you have any quantum operations, which are usually known as quantum maps. This is the Krauss representation of the quantum map. So any Krauss operator can be discretized. That is, it can be broken up into X, Z, and Y Pauli operators, because any 2x2 matrix is spanned by Pauli operators and identity operator. And what happens when there are some photon loss, especially the dual rail qubit? The dual rail qubit just moves out of the Hilbert space. So it's not at all in the qubit space. It's just out of the qubit space. Oh, next, the question is, if we have so many faults, can we do something fault tolerantly? So even with all faults, is it possible to perform some universal gate set operations on this optical platform? The answer is certainly yes, we can do it. And for this, we need to build a fault tolerant error correcting codes, which look like lattice here. So this is known as Rosenbach, Harrington, Goel lattice after the inventors. So these lattices are made of like thousands of qubits. So our task is to perform, my task is to show that using small qubits like 3-qubit states, we can build these large lattices. So let's learn how much error can be tolerated. So I just showed like the Bell state measurement failure. So if the Bell state measurement failure is around 14.5%, that is, if the Bell state measurement is successful by 85%, we can still perform reliable quantum information processing on this lattice. So our goal would be to improve this 50% success rate to 85+% success rate, or say like up to 9. We want to bring it up to 90%. So how it can be achieved, we'll discuss about that later. And apart from entanglement failure, the qubits can also be lost, and it can also have Pauli errors. So this plot from previous works show that we can tolerate up to 6% or 0.6% Pauli error if we do not have any losses, qubit losses, and if we have qubit loss up to 25%, we can't tolerate any Pauli error. So if your system is within this correctable region, you can perform fault tolerant gate operations. So how can we protect our qubits against losses or against any kind of Pauli errors, flips, bit flip errors? So what we do is we have this encoding circuit. We have a quantum state. We add 2 extra ancillary qubits. Then we perform control NOT gates. Then the initial state is transformed to this state. This is known as reputation code. So earlier, what are the logical operations on the state phi? So X and Z, they are the single qubit logical operations. But with this expansion, the new logical operation is x1, x2, x3, and the new logical operation is z1, z2, z1 or z2 or z3. So what have we done here? So we have improved the redundancy. So on qubit 1, if you measure z, or qubit 2 or qubit 3, you'll get the same information. So what does this mean? If qubit 1 is lost, you can still learn about logical Z operation from qubit 2. And if both Z1 and qubit 1 and qubit 2 are lost, you can still learn about the logical Z operator by if you get access of logical operator from the third qubit. So what we have made the logical Z operator robust against flips. So losses and also flip. So flip, if Z1 value flips, you can go for majority voting and do and guess the right value of the outcome. Similarly, if you rotate the basis, that is, if you perform a Hadamard here and you rotate the initial state of the ancillary qubits and then perform the same circuit, then you will get robustness against the logical X operator. Now, from the first circuit, you have robustness about logical Z operator, and from the second, you have robustness for the logical X operator. So we want a state which provides robustness against both the for the both operators. So we perform something like this, which we call it as concatenation of the codes. That is like putting two codes together so that they work appropriately. Now the new logical operators are this, and you can see that now you have redundancy both for X logical operators and Z logical operators. So this is how we protect against losses and Pauli errors. But remember, we still have a Bell state measurement or an entangling operation, which is less than 85% success rate, which is the threshold value of success rate we need. How can we improve them? So we can perform Bell state measurements, which we call as encoded Bell state measurements on these quantum parity check codes, that is concatenation of repetition codes. And we can improve the success rate up to 1 or 2 power n minus m. So you can just see like if n and m are 1, the success rate is 1. And if nm is 2, the success rate is 75. Then if it's 4, nm is 4, the success rate is like 80, 85 something. And if it is 5, then it's 92%. So we have already hit 92% success rate if we can generate large enough states. So there is no need for only quantum parity check codes. There are also other kinds of codes which can do the job. These are like 7 qubit Steen code, but constructing these codes could be a difficult task, may not be a scalable one. So we would stick to quantum parity check codes rest of the talk. So these codes are not just useful in quantum computing, these are also very much needed in quantum communications. I'm sure like you guys heard from Akshata talking on quantum communication. So in quantum communication, you transmit qubits, which are extremely lossy through the extremely lossy lanes through optical fibers, which are lossy. So if you encode the states, loss can be reduced and you can reliably do some sort of quantum cryptography across really large distances, like up to you can perform faithful cryptography up to 1,000 kilometers or even 10,000 kilometers, provided you construct larger and larger quantum codes. That is, you make this system big and big. So I told you about measurement-based quantum computing model, where there are two types of models for fault-tolerant quantum computing, in general quantum computing. One is circuit-based model where you apply all the unitaries, and the second one is measurement-based model. And measurement-based model is more suitable for optical platforms because you just need to generate a big state initially and then keep performing measurements. And these measurements would end up performing some gate operations for you. So this is the idea of measurement-based quantum computing. For measurement-based quantum computing, all you need is you need to generate a large cluster state in advance. So state preparation gets complicated in this model. So these are the examples where you can generate a two-dimensional graph state. On that graph state, you can perform control not gate if you perform your measurements in appropriate basis. So you keep performing measurements, single qubit measurements, and these two qubits at the end, they get entangled and they would be in a bell state. So how can we go from single photons to building cluster states or lattices like this? So here are some insights about the single photons. So you can generate single photons in a heralded manner, but the success rate of single photons coming out of this would be like around 10 to 13%. The maximum possibility is 25%, but if you operate your parametric down conversion source at 25%, it could be extremely noisy. So we want to reduce the noise, so we operate it at around 10 to 13% success rate. Because the success rate is very small, we need to multiplex it. We need to put many sources together, and we need to use lot of optical switching so that most of the photons arrive at given output with high probability. And of course, there are also some other techniques other than parametric down conversion. You can use quantum dot based sources where you can get single photons at very high rates, but even they have their own difficulties. So they would be plagued by a lot of Pauli errors, especially like if you're trying to interfere photons from two different quantum dot sources, it would be like very poor interference, because one can't fabricate a quantum dot of quantums of constant size. Each quantum dot would be of different sizes, so that each photon emitted would be having different frequencies. So an attempt to interfere them would not be very successful. That's the drawback. And once you have single photons, you can generate free JZ state using this kind of optical circuits. But the success rate again is 1/32, which is extremely small. And now people have been using other techniques to generate larger entangled states, like four. Understanding how we can generate single photons and free JZ state, let's see like how we can build quantum parity check codes. Yeah, these things can also be like this JZ generator states can also be put into a 5 millimeter chip. So everything I'm explaining is possible on chip. So yeah, this is the advantage. One can miniaturize all the optical components. So given 3 JZ states, we showed that you can build a very large quantum parity check code states. And once you have quantum parity check code states, you can perform encoded Bell state measurements and build something known as star cluster states. So it's not essential to build these lattices, these large lattices, but if you have access to star cluster states, you can just assemble the star cluster states appropriately and build the lattice layer by layer. So these are here I'm showing 2 layers of the lattice. And with failures, remember, even the encoded Bell state measurement is not perfect, even it fails. Whenever it fails, you would have some defective lattices. Some edges may be missing and some edges may be misplaced. So all this can be overcome on this fault tolerant lattice. So we performed some simulations. For decoding, we used minimum weight perfect matching algorithm, and we showed that as we increase the size of the quantum parity check code, we can have better loss thresholds. So in this work, which was published in NPJ Quantum Information, we showed that when n is 5 and m is 4, we can attain a threshold of around 8.5%, which is quite high. And all this comes at a lot of overheads. To construct a lattice which can give very small errors, which can give really small errors, we need to spend around 10 power 5 number of JG states. So we need to generate 10 power 5 JG state so that we can achieve a loss tolerance of 8%. So I work for Orca Computing. Even Orca Computing has a very similar model for fault tolerance, and we showed that if we have large enough quantum parity check code, we can tolerate up to 12% loss rate. But the resource overheads are extremely high for this. If one is concerned about resource overheads, one can use hybrid qubits. So these are the two works about hybrid qubits. So with hybrid qubits, one can figure out that around 10 power 4 GAG states are enough to perform fault tolerance, but the fault tolerance rate is small, up to not 8%, 0.8%. You have loss tolerance decreased by an order of magnitude, but what you have gained is you have reduced your overheads. So there is always a trade-off between loss threshold and resource overheads. More you spend, more loss threshold you can have. And yeah, I just showed how we can perform fault tolerant memory. So all the lattice I showed, it was just ideal. It was not performing any gate. But if you need to perform gates, you need to iterate the lattice in some special states, and then you can perform C0 gates on the lattice by performing some measurements, single qubit measurements, and you can achieve universality by something known as magic state injection. So I showed in the previous slides how the magic state looks. So this is how magic state looks, and one needs to distill this magic state, because if we prepare a magic state, it's never e power I pi by 4, but it's plus or minus delta. So you need to purify it. So the magic states can be purified by using these complex networks. So magic state is the most resource demanding part. Magic state distillation is the most resource demanding part of the quantum computing process. And so that's why any quantum algorithm is characterized by how many magic states it needs, or how many pi by 4 gate operation it needs. So once you inject a magic state and perform some measurements, it would be equivalent to performing non-Clifford T gate operation. So this is just to provide some idea about how big a quantum computer could be or should be. So here we are there was this work, feasibility of accelerating homogeneous catalyst discovery with fault tolerant quantum computers, which was recently published. and they showed that if we can simulate a nitrogen fixation process, how much quantum resources do we need? So they characterize they characterize the performance of the molecule MON2, which is a nitrogen fixating catalyst, and they showed that it is needed to have of the order of 10 power 10 Toffoli gates. Toffoli gates are another Clifford gates. Toffoli gates are similar to 5 by 8 gates, T gates. So 2 T gates roughly on an average makes up for a Toffoli gate. So if you are calculating the complexity of this quantum algorithm, so it would be like 6.2 into 10 power 10, and you also need 10 power 6 physical qubits. So these are like fault tolerant qubits. Like you can have 10 power 6 such lattices. A single lattice would take something like 10 power 6 number of 3 GHZ states, and an algorithm or a quantum computer would take 10 power 6. So in general, you'd need like something like 10 power 12, at least 10 power 12 number of GHZ states to perform these quantum algorithms. So that's how expensive it could get, and that's how scalable the systems should. And ending my talk, this is our so we probably had a different viewpoint. Instead of generating the star cluster, the new scheme just generates 2-qubit states. So these 2-qubit states undergo something known as GHZ measurements, 4 GHZ measurements, which is again probabilistic, but still with these kind of operations, we could manage to hit around 20% loss, 12% loss threshold. So this is the state of the art as per my knowledge, and what is the future direction. So you see throughout the talk, the shortcoming was uh, the main shortcoming was probabilistic entangling operations. So can you improve the success rate of entangling operation by using something as non-linearities? Certainly yes. There was some work which showed that from 0.5 to you can increase the success rate. If there is no loss, of course you can make the Bell state measurement deterministic, but it is always plagued by some losses. So you can improve the Bell state measurement success rate up to say 80%. Once you have 80% success rate, you can concatenate the Bell state measurements with the quantum parity check codes, and you can do all your fault tolerant quantum computing on those kinds of platforms. Now, another research direction is like LDPC codes, which stands for quantum low density parity check codes. You saw that all the lattices I showed, it only encodes a single bit of information, single qubit of information. So which is not resource intense. As I increase, which is not resource efficient. As I increase the size of the lattice, the qubit encoding rate goes to 0. So we want to have something like qubit encoding rate to be a constant. So this is possible by quantum low density parity check codes, which is really active area of research as of now. And we also need better decoding algorithms. So as I mentioned, the classical computers have to keep up with quantum computers. They have to be faster, or at least as fast as quantum computers. So we need better decoding algorithms. With this, I finish my talk. Thanks for inviting me. Yeah, if you have any questions, I would be open to questions.
Thank you very much, sir. Such a wonderful presentation. There are few questions in the chat box I would like to read for you. Can you please throw some light on phase and flux superconducting qubit?
That's I'm really sorry about it. I don't work exclusively on superconducting qubits, so my knowledge on superconducting qubits is not very deep. So all I know is they form Josephson junctions, and it's a tank circuit, oscillator tank circuit. So where the current flows in one direction or the other direction, and these are the two possibilities of the quantum state, and you can have a qubit with such electric flux going through the circuit, tank circuit. Yeah, that's it.
Thank you, sir. I request if our other resource experts like Anant S. Naik sir can reply for this question. Or Srinath sir.
To the next question, but it is in fact a very good talk about the instrumentation, how to create a single entangled photon, two photon pairs, all those things. I mean, I would say that Omkar has done an excellent job to know more about the instrumentation. I appreciate him. We will see, sir, future. Take up the next questions.
Thank you, sir. Yes, sir. Yes. Sir, any reference material about phase? Reference material about phase and flux superconducting qubit to make undergraduate students understand this topic? Any
I
reference
think
material?
maybe Omkar, you can clarify. Many people are thinking supercomputing. You have to
Yes.
clarify that.
Okay. If that's the confusion, so superconducting qubit is just a platform where you can realize a qubit. It is called superconductor because um, when you in certain materials, when you reach extremely low temperatures like around 0 Kelvin, so your resistance literally becomes zero, and once you excite a current within a circuit, it never stops. It keeps circulating within a circuit. So as I said, like it's a tank circuit. So you have inductance and capacitance. The current just keeps oscillating without any resistance. So this is just a name. This phenomenon is a superconducting phenomena. So, and this is not something related to supercomputer. So this is just one of the platforms. You can realize the qubit in any other platform, any quantum mechanical platform. Also, last week, Dr. Prabhu showed from IIT Dharwad showed about oscillator, harmonic oscillator, and how you can have qubits with harmonic oscillator. Any quantum system works as qubit. Yeah.
Thank you very much, sir. What is R mentioned in the C0 gate, sir? In your previous presentation.
R? Okay.
What is R mentioned in the C0 gate? Yes, sir.
Okay. Can I just share it again?
Yes, sir. Yes, sir. You can share it.
Yeah. So, yeah. So here R is the reflectivity. So this is not half of beam splitter. This is unbalanced beam splitter, and I have also put a figure where you can have two balanced beam splitters and change the phases and perform some imbalanced beam splitting. That is like with probability 1/9, like R square. I guess this is how things work. It's reflected, and with 1 minus R square, it's transmitted. So that's the idea. Yeah.
Thank you very much, sir. Sir, how can we realize the quantum gates through flux qubit? Qubit charge through Josephson's function junction. Good.
Quantum gates. So I'll just repeat my answer again. So this talk was not exclusively on Josephson junctions and superconducting qubits. It was exclusively on optical platforms. If you have questions about optical platforms, I can explain in detail.
Yes, thank you, sir. Thank you, sir. Now, our chair professor, Dr. Usha Devi, madam, has joined with us. Welcome you, ma'am. If madam,
Thank you.
yes,
I couldn't join earlier, sorry. I will listen to it in YouTube series.
okay, ma'am. Sir, any other applications currently these optics for quantum information processing is used, and what are the initial costings?
What are the initial costings? So
Yes,
if
State-wise.
someone wants to,
Yes, sir.
yeah, if someone wants to set up a startup,
Yes, sir.
as I understand, you need some basic optical elements, like photon source. Getting a single photon source is extremely competitive. Even now, people are struggling. Even after all the research, getting an appropriate single photon source is extremely difficult, and you need extremely good detectors, and say like nanowire, superconducting nanowire based detectors. So you need to place them in cryogenic temperatures. So you need a large fridge, cryostats, to cool it down, and you need a lot of optical elements like beam splitters, phase shifters, and such things. If you have availability of all those things, and I'm not sure like if I can quote some numbers, like how much rupees, how much crore rupees they would cost. I don't have much idea about them. I don't work with the finances of the optical elements. But if you have these elements, and if you have expertise to put them all together, so putting them together is extremely challenging. Even if you have good source, can you just make sure that your photon is going through the elements through which you want them to move, are all extremely challenging. I would rather say, like, more than money, you need human resource. So human resource is the most important thing. Money then is the secondary thing. Once you have human resource, really expert people who can handle these things, quantum computing can happen, because anyone can. If people are promising, there are investors who can invest in money. Yeah.
Ready to invest. Yes, sir. Very good. Thank you, sir. Thank you very much, sir. So if any other questions, I request participants to raise their virtual hand so that I can unmute them. You can speak to sir and get clarification about your queries. If there are no
Yeah.
questions,
Yeah. Can I just
yes, sir, please.
end my talk? So Usha ma'am is here. She is the one who taught me quantum optics. Going out of the way, it was not a curriculum, but still she taught us the quantum optics. So I have developed on her knowledge of quantum optics. I'm really thankful for her.
Thank you for mentioning it. It was a
Many of
joy
the people,
learning
Usha is
together.
mother of
Thank
quantum
you.
physics for many people.
Yeah. Yes, certainly yes.
Anand sir,
But she will
any
be always behind. She is not well known. We should make her well known.
thank you, sir.
Okay.
Thanks for the comments.
Thank you, ma'am.
So, now I would like to conclude the today's first session. Thank you very much, sir, for accepting our invitation and delivering such a wonderful talk on
No,
on
you
this.
need to mention his time and date where he is awake and delivering the talk for the benefit of
No,
the many of
sir is
the
in India
audience
only, I think.
waiting for.
Sir is in India only.
Okay, good.
Isn't it, sir?
Okay. I didn't. Okay, please proceed, sir.
Yes, sir. Yes, sir.
Omkar, you
Thank
are
you very much.
muted. We couldn't hear you.
Oh, I was just revealing my location, mysterious location. I am somewhere in Shivamogga district, Hosnagara Taluk, Sampekatte.
Oh, we didn't know that you are doing. Okay, good, sir. Good to know your location revealed. Thank you.
Yeah.
We were worried about the network issues. Somehow we got good network. Only in between 2 to 3 times it got disconnected, but fortunately everything went well. So thanks, and thank you very much, sir, Dr. Omkar sir, on behalf of KSTA and on behalf of all our quantum team here, and all the students and teaching faculty. Thank you very much once again. Thank you, sir. Also, I would like to thank our chairperson, Dr. Usha Devi ma'am, and Dr. Srinath sir, Dr. Anantyas Naik sir, who have joined with us, and our KSTA technical team and non-technical team, who are behind this webinar series. And last but not least, I would like to thank all the participants who have joined with us in both the platforms, without whom this international webinar series wouldn't have been successful. On their request only, this is a second series we have started. The first series was very successful, and with this we would like to conclude. And tomorrow we have Dr. Anand sir's talk, which is on characterization of quantum entanglement using entropic criteria. I request all of you to join with us at 3:15 or 3:20, so that we can start the session timely. Thank you. Thank you once again. Thank you one and all.